All right, students, so this is going to be a quick video on spanning trees. So we've studied, we've studied Euler circuits and paths, which basically was said we had to connect all of the edges of a graph, right? So like if we think about this tree as a graph, it would have to connect all of the edges. And then we studied Hamiltonian circuits and paths, which basically said all of the vertices would have to be connected, right? In either a circuit or a path, and you couldn't like retrace your steps in either of those. Spanning trees are a little different. All spanning trees are used for, think about like networks, or phones. Like we wanted to be able to call everybody. So say there's a squirrel that needs to be able to get to every branch on the tree to get that acorn. This is a Joshua tree, so that's not really, relevant. But anyway, so there's a squirrel here, and he needs to be able to get to the acorn over here, right? So he can get to every branch, every vertex on this tree just by following these branches around. So this is an example of a spanning tree, and it has actually a connected graph, meaning there are no disconnections. Like, so for example, I can't have a branch just hanging out over here, cut that off and there's a separate graph. So the graph has to be connected. So that's what we're going to look at. So here's the definition of a spanning tree. It is a connected graph that has no circuits, and there's a path from every vertex to another vertex. So that's exactly what we were just looking at on that Joshua tree there. And it's okay to have degrees greater than 2. So when we were looking at those Hamiltonian paths and circuits, you couldn't have a degree greater than 2 because you couldn't go to the same point twice. But it's okay for spanning trees. So for example, if we wanted to create a spanning tree here, we could just connect it this way, right? So if I'm here, I can get to any other vertex. If I'm here, I can get to any other vertex. If I'm here, I can get to any other vertex. So that's all that that's saying. Here's another example. That one would work, or that one. So these are all types of spanning trees with these 4 given vertices. Now, what we're also going to look at is the minimum cost spanning tree. So what is the cheapest way for us to connect these points? So like if we had some cities or something that we wanted to connect by phone or internet or something, we want to create some sort of pipeline between these cities. What's the cheapest way to do it? So that's a minimum cost spanning tree. And we're going to use Kruskal's algorithm. And it's similar to the sorted edges algorithm we looked at using the paths before. So what we do is we select the cheapest unused edge in the graph, and we continue adding the cheapest edge unless it creates a circuit. So this time you don't want any circuits. And you repeat until a spanning tree is formed. And that just means that all the vertices are connected to an edge. So let's look at this example here. So the first thing I'm going to connect is the cheapest one, which is 4, which is this New York to Philadelphia. The next cheapest one would be 5. Then the next cheapest one is 6, but I can't do that because that's going to close it off and create a circuit. So I'm going to have to erase that. That was a mistake. So actually the next cheapest one would be this 7 down here. So that's the next cheapest. And then 8 is going to be the next cheapest after that. And then 9. Oh, wait a minute. I've created another circuit. Let me erase that. And actually, I don't have to connect anything else at all because I actually already have a spanning tree. Look, I can get from Chicago to any other city I want. Same from Houston. I can still get there. If I'm that squirrel, I can crawl along all the branches and get to every other vertex. Not a problem. It's already done. So the minimum cost is I just add up all of the costs of the edges. In this case, it was 24. So it's 24. That's positive 24, by the way. Let me make that an equal sign. So let's look at another example, and sometimes we'll see these graphs written as tables because sometimes if you have so many vertices that it gets too confusing to look at as a graph. So they actually put it in as a table, so now we have this graph here represented as a table, and it is a complete graph. Notice that all of these are vertices, and they're connected to every other vertex. And so, for example, the line segment AB is represented by this 21 here. That's the cost of that edge. So we can go ahead and use Kruskal's algorithm again. We're just going to go through and find all of the cheapest edges. Notice this graph is actually symmetrical, so I can actually just ignore the top part of the graph and just focus on this bottom part here. So that's what I'm going to do. The cheapest edge is 1, and I'm going to go ahead and draw the graph out as I go, just to make sure that I've created a spanning tree. The next one would be 5, and that's BD. So now I have ED and BD. The next cheapest one is DF. So I've connected that up here, DF. Then EF is the next cheapest. But if I actually connect E and F, I've created a circuit. That's no good, so let me erase that. So let's take a look. The next one is actually this AE here, this 15. That's the next cheapest. And then the next one is this 16. Oh, but wait a minute, DE. If I connect DE, that's also going to create a circuit. That's no good. I have to erase that. So 18 is actually the next cheapest. And now I'm done. Because look, I've connected everything. I have all 6 points, A, B, C, D, E, F, represented on my graph. And I can get to all of the points if I want to. I can get from B to E, I can get from B to A, I can get from B to C. Not a problem. I can make a path to any one of those. And so the total cost for this graph is 45. So hope this helps, and please let me know if you have any questions. And by the way, we're listening to Joshua Tree by YouTube.